we will get into basically going over the permutation problem in just a bit, but I also want to just draw your attention to my YouTube channel for just a second, not because I need your likes and subscribes. Far from it. Let's see. We have this. I have this playlist called
Today I want to talk
called Worth Watching, which is it's just a compilation of videos I occasionally find online, and then if it strikes me enough, if I find it on my I have multiple YouTube accounts. One where I post personal stuff like music compositions, and then this one over here. I don't mention this again because I don't want your likes and subscribes. In fact, if I could disable advertising on this, I would. And if you look at my plugins, I literally have an ad blocker and something that people contribute to denote to track where sponsor segments are in YouTube videos, so that we can skip over them. Like, that is how much I don't like advertising. It's especially bad when you have a kid. I don't want him to be necessary. They're so easy to. People in general are so easily susceptible to advertising. Anyway, point being is I've got these videos here, and I consider them worth watching if you want. Some of them. This is more hard computer science. This is more puzzles. This is hard computer science. This is really interesting kind of ideas of behind video games. This is way more about text than you'd ever want to know. Again, non-Euclidean stuff is weird. If you're interested in kind of AI stuff, this might be interesting, although it may be out of date because that moves so quickly. And then things about, hey, writing stuff in Lua and in Pico 8, because if you want to make games, you should start small and focused. Don't try to make a big game on your first outing. And doing something small in Pico 8 can be a lot of fun. Pico 8 being a fantasy console that doesn't exist.
Isn't Factorio coded in Lua anyway? So you could go absolutely nuts with, like, if you start small, you can, like, it's incremental, meaning it's like you can build on top of it.
This one, well, Pico 8 specifically is meant small. Like, it's got a 8192 token limit.
Gotcha.
And so, but it's literally designed to kind of emulate the issues of having that small focus. It's literally the amount of stuff you can stuff into a PNG of a certain size.
Good point. Okay.
And then this video is about Balatro, which I haven't had the chance to play, but that was written in Love 2D, which I've got. If you need tutorials, I can point you to Love 2D tutorials.
You'll lose time to that game.
I've not tried it. Again, I have my own poisons. Again, besides RimWorld, I'm enjoying the Dragon Quest III remake because if you are not obsessed with Dragon Quest like I was as a kid, then I don't recommend buying it for the full $60, by the way. I bought it for the full $60 for myself because I played so much Dragon Quest III, Dragon Warrior 3 as it was called, back then. So as a kid, so that game had a lot of sentimental value to me, and so but it's a very good game, and I enjoy what's been done with it. Anyway, so enough of that. Let's get into the meat of what we need to do today. So we were working on today. So I noticed some of you did make an attempt on your is permutation. Now the fun thing about is permutation is that there's a lot of ways to do it, and this is not the first time. This is not the last time we'll be tackling it in the semester. The more optimal solutions involve using something called a hash map, something you may have used a hash map already in a prior programming language like Python, when it's called a dictionary in Python, or if you've programmed in Lua or another language, you may have heard it called an associative array, or just a map. They're kind of all names for the same thing, and we get into that later in the semester. It's a lot of fun. You'll learn, again, the pedagogical model of how they work. You could even build one that will work in constant time, just not as efficiently as everything else, as the optimizations the computer will do. So anyway, but right now we're just using with the tools we have, and I'm going to go over a couple different solutions, which is my habit when we do this. So public static Boolean. So this is going to be we're taking in. We don't know what this is, so it's an E, and it's going to be E, and it's going to return a Boolean, is permutation. Again, what we're doing here with these is that we are saying we don't know what type of what the type inside the list is, but we want to, for simplicity's sake, assume that it's all the same type. So a list of strings here. So list, and I'm going to call this A, capital A, just for brevity. I normally do not like giving stuff like A and B for this. But again, brevity here, and we're kind of limited, and we're already working in something abstract. Now, once again, we have an error as soon as we start because we promised to return something and we have not written our return statement yet. Not really an error, but the compiler is already getting ahead of itself. So we got to think to ourselves, are we going to assume that everything we get passed is a permutation or not? And I think it's easier to, you can think about it, but if you give it some thought, you might think, well, it's easier to assume that these things are a permutation and then try to disprove it. So I'm going to return true and try to prove that it's not. Occasionally I'll miswrite true with a capitalization because it's capitalized in Python. So switching between two programming languages can be a bit weird. Once again, permutations work like this. Wolf and flow are two permutations of the same letters, right? Whereas if I were to do A, B, and B, A, those are also permutations, but A, B, B are not permutations because there's a different count of these letters, right? These two have two A's and one B, whereas line 23 has one A and two B's. So permutations, again, it's the order and the counting that matters, okay? So this leads us to, though, so let's go ahead and just write down an assumption we can make. Not an assumption, but basically a check that we can make that serves as an assumption for everything else, which is that we're going to check to make sure that a.size and b.size are the same. Yes, I know I'm writing a not equal here. If they're not the same, we'll do something, right? If a.size is not equal to b.size, if they're different, well, they can't possibly be permutations of each other because we're going to have different counts of items no matter what, right? Return false. Now, I'm going to go ahead and do a mini 30-second rant here. In Java, you have different ways of telling the sizes of different things, and that's one of my design irks of Java. If you have a array, you call it array.length. If you have a string, you call it string.length, but with parentheses. And if you have basically any kind of collection, which is all the stuff we're learning, all the data structures we're learning, such as a tree or a list, you call it tree.size or list.size with parentheses. This is not a trick question that will be on the exam because it's one of those things that if you mess up, it's super easy to fix. I don't like to test those like things that you can figure that the compiler can help you figure out because I find that less than useful. But what we got, but basically this is an intrinsic property of this, as opposed to this being a method that returns an intrinsic property. So I don't know why they decided this design choice. And then the size, the logic behind that, I assume, is because trees don't really have a length. They have a certain number of nodes in it, right? Or heap, which is just a pile of stuff, right? And so you don't really necessarily know what the size is of that. It doesn't really have a length. Sorry, you know what the size is. It doesn't have a length. Can't really give it a length. Length is meaningless because it's a pile. And size is kind of more of an abstract term, so I assume that's why. Python don't care. Python did the correct and said, hey, we've got a length function, and you just toss something into it to figure out how big it is. So anyway, rant over. Okay, so now that we know that the sizes of these two things are different, all right, are the same, we can start our algorithm. And what we need to do in order to tell if something's a permutation is that I have to go through every item in here and count the number of times it appears in the second one. There's other ways to do it, such as we could remove, but I try my best not to modify anything. And I also wanted to do a solution that didn't require us to make any what what we'll call auxiliary data structures. In other words, we didn't want to make, I didn't want to make any additional lists. We could, but didn't want to. So what we're going to do is we are going to do, so I'm going to write a for loop, and the way I'm going to do a for each loop. The way we read this is for each, I'm going to call this like this. For each item of type E in A. Okay, you read this colon as an in. For every item of type E in A, in list A. What are we going to do? And effectively, this will do the same as what I'm about to write, which is a for I loop. For, and IntelliJ is pretty good about that. And effectively, what I've done in this loop over here is I've done in this short statement what I just did over here. Make sense? So for every item A, the first thing I have to do is count the number of times it occurs in A. So that's what this inner loop is going to do. It's going to count the number of times it occurs in A. A is equal to 0. And then we ask if item A is equal to A, not A, is equal to item. Those two things are equal, count A plus plus. Make sense? So we're going to count, so for every item in A, so this is what makes this one permutation a bit weird, which is that I have a loop going over A, and then inside that I have another loop going over A. Right? For every item in A, I'm going to go over every item in A and count the number of times that item appears in it. Okay? Then I'm going to do the same for count B. Count B. And I can just copy paste that one, and as long as I'm careful about what I'm doing, I can just replace all the instances of A's with B's. Usually it's better to rewrite this than do what I did, right? Because it's so easy to accidentally miss one of them. Do as I say, not as I do. But I've done this example enough times that the risk is rather low. So count the number of times it appears in A, count the number of times it appears in B. Then, if count A is not equal to count B, if they've appeared different a number of times, return false, because they have a different count, they can't possibly be permutations of each other. So this is solution number 1. And you can see it's a bit messy, right? Or not messy, but like it's
There's a lot going on.
Yeah, it's a lot going on. It's a bit weird. You've got this outer loop, and then you've got an inner loop that goes over it. There's also this, now, space efficient, yes. It's very actually space efficient because it requires very little additional space. But however, this requires us to go over for every item, we have to go over it in both list A and list B, even if it's an item we've already counted before, right? Right, let's go to this example. The way I've written the algorithm, I'd have to count this item. So we're going to start with this item. I'm going to count how many times A occurs in here and count how many times A occurs in here. Then we go over to this item. I'm going to count how many times A occurs in this list and then count how many times A occurs in this list. So I've just repeated my operation. I'm not really keeping track of it. But it's a solution. And honestly, a lot of the times when you're going through interviews and stuff like that, they just care about getting a solution, then refining to a better solution with kind of the tools you might have at hand. All right. One common solution that students come up with for doing this one in a bit more of an efficient manner is the idea of, well, if I just put, if these two words are permutations, I can actually just like sort them, right? If I sort them like this, sort them alphabetically, like that, then I just check if they're equal. And if the sorted versions of them are equal, awesome, we're great. Make sense? So sort them, check if the sortings are equal. That's actually a much shorter solution and requires some extra knowledge on our part, but it's a good step. Yes?
I took that approach and it's the entity type's different though. Instead of a E, it's a T. I wasn't sure that's like.
Ah, yes, I'm going to go into that. So that's what I require when I say it requires some additional stuff. That's what I'm talking about. So we're going to go over how to do that properly here. So public static E. So I'm going to start by writing some stuff that's going to give me some errors, but I know it is going to. Boolean is perm2. Okay, list E, list E A, list E B. Right? Okay. And then the next step is we are going to assume, again, that the two are not that. So my plan is that I'm going to, again, when I'm given inputs, I don't like to modify them. And sorting, so let's first look at how we do sorting. Sorting is done by this operation. Collections, so just like there's an arrays class, which you can use array, and in case you haven't seen that, the use of that is that the easiest way to print an array or get a string representation of an array in Java is to do arrays.toString, which will convert that array into a string. Much like there's an arrays class that has tools for working with arrays, there's a collections class, which has tools for working with collections, which is what this is. And you can use something like collection.sort. And it says it's taking a list of type T. That's what the T means, just some kind of type. And you take in that list and you sort it. And that has an error. I'm sure that has no possible implications for this going wrong yet. But anyway, we'll go ahead over here and just kind of address the first issue, which is I don't like to modify these. Right? I'm going to go ahead and create two new lists. List E sort A, or sorted A, is equal to, or actually, I'm going to call it, yeah, sort A, because that sounds more like a command. I'm going to call it is equal to new array list, and I'm going to create a new one for B. And I could do this in one line, but I'm splitting it up, just simply so I can show you. And then what I'm going to do is I'm going to say sort A dot add all from A, which will take everything from A and add it in there. It's just basically doing repeated add operations. Sort B dot add all B. It does, these things do work under, again, the principle of least surprise, doing the least surprising thing. Are updated but never queried. Yeah, it's warning me, hey, you're adding stuff to this and then you don't do anything with that. Modern compilers are pretty cool with that, about this kind of stuff. And that's kind of the power of using using a language like Java that has all these kind of measures in there to help you, from going off the rails. So sort A, sort B. So now we actually have to sort them. Collections dot sort A, and I'm going to, again, disregard my own advice and continue on despite having an error, because I know what I want to do, which is I want to sort A and sort A, sort B, and then check, and then rather than returning false, I'm going to just say sort A dot equals sort B. Make sense? I'm going to sort them and then check if they're equal to each other. However, my error is coming up from here, saying I can't. What is it saying? So now the compiler in this case, or the IntelliJ is being kind of less than useful with this one. It's hard to see, but it says list required type, list T, provided, list E. So if you just read that bit, you might be thinking, okay, what if I replace all my E's with T's? You'll find that that does not actually change anything. It's not the letter that matters. The letter is, again, just a variable. So changing your variable name isn't going to actually affect anything. It's the second bit of that that makes that error message that we care about. No instances of type variables T that exist so that E conforms to comparable ? Super T, which honestly, unless you listen to this makes no sense except for like in a minute from now, which is what I'll explain. Sorting things require things to be well ordered. In other words, it requires things to be put into an order. I think it's well ordered as opposed to partially ordered. I'll have to double fact check that. Those have very specific mathematical terms. But the point being is that sorting requires things to be put in an order. And not every type can just natively be put into an order, right? Think of scanners, for instance. Integers are easy to sort, right? Just lowest to highest. Same with strings, alphabetical order. But scanner, how in the world would you sort scanners if I was given a list of scanners for some reason? Maybe by creation time, but that's not necessarily an obvious kind of sorting way to sort them. Or memory address, also not necessarily obvious. Both are kind of valid ways to sort an unsortable object. So what sorting demands, if we go and look at it, is that it demands this weird thing. It demands that natural ordering, not well ordered. So natural ordering. All elements in the list must implement the comparable interface. In order to sort things, things have to be comparable to one or another. Comparable is an interface. Very simple interface. It has one method in it. Things that are comparable implement the compare to method, which allow things to be put in an order. Integers are comparable. Strings are comparable. And I'll show you what that is after I kind of solve this issue. But the point being is that things have to implement that compare to. Comparable basically is the way of saying, hey, this is something that Java can sort naturally. So, and the way we can just simply put this in is we say E is that this will come in, and this will not be something you have to remember until we start going over in trees like week 8 or so. And then it will come up and it will be part of the lectures that I do, so no worries. E extends comparable E. And we don't need to do that super syntax that they had in there. That's more correct, but I don't want to overcomplicate it. What this means is that now basically we're saying, hey, you're going to get a list of generic items. What I'm going to guarantee is that the list of that type, they're all the same type, but they're all comparables, right? There's a restriction on what we can pass in now. We can pass in a list of strings, we can pass in a list of ints, but scanners aren't comparable, so we can't pass in a list of scanners. Make sense? And so now it shuts up about that. So what does the compare to method do? Compare to is very simple. And I'll use integers for this because integer A is equal to 5. 5. Integer B is equal to 10. A dot compare to B. Okay? And let's go ahead and print that out. Okay? And kind of just test and see what happens. It's running now. Parsing. Come on. It returns -1. If on the other hand I do B dot, whoops, not caps lock B, B dot compare to A, I'll get 1 instead. And if I do A dot compare to A, I'll get a 0. So what's going on here? The way the compare to interface works is that it specifies, hey, you're going to get an A and a B. You're going to say object is going to compare to the other object. If the original object comes before the second object, that other object, return a negative number. So in other words, if A is less than B, give me a negative number. If A is greater than B, or comes after B, return a positive number. So here we'll look at A. So here we'll look at this case, 5 is greater than 3, so we're going to get a positive number, right? 1 is a positive number. And if they're equal, you get a 0. Now, now it specifies only positive or negative. And the reason for this is that actually we can do things like this. String S1 is equal to, let's just keep it simple, A. String S2 is equal to B. Let's go with D, actually. D is in dog. And what we're going to do is we're going to do S1 dot compare to, and that's should error, right, because you can only compare to objects of the same type. That's kind of even though they're both comparable, you can only compare to objects of the same type. That's kind of the restriction. And this gives us -3. A dot compare to S1 dot compare to S2 gives us -3. It gives us a negative number, but also we encode additional information for strings, or the developers decide to encode additional information. -3. Why? Because A, B, C, D. Right? It's 3 before a D. It's not true necessarily for integers, but you have leeway if you ever want to implement your own compare to. So compare to is very easy. You don't really need to use it, but it's super helpful. And this is a much more efficient way of doing it. It just required you to do two things. One, you had to know how to use this. And two, this does put a restriction on the types of stuff you can put in. Make sense? So this works on everything, including scanners. This will only work on basically things that are comparable. But it's more efficient. It will run as we discover in n log n time. Our next week's assignment will be much more like a math class, but I promise you we'll have some puzzles in there too. So it won't be so bad. And it's one of those where I'll say, just go and look at Wikipedia at this specific puzzle. So it'll be interesting. All right, any questions on this before I start going around the class? And I will upload this in case you weren't able to, in case you weren't able to copy down one of the answers. No? All right, with that, I'm going to go ahead and start walking around and helping people.